The next speaker is Dr. Paula Abdullah, and she studied chemical engineering at the National Technology University of Mendoza in Argentina. Then she obtained a PhD in material science at the University San Martin in Buenos Aires. Then she moved here at SRF as a postdoctoral researcher, and now is currently employed at the ETH of Zurich. Her research is focused on the relationship between structure and performance in catalysts, fuel cell, and carbon dioxide sorbents. So, please.
Good morning. Can you hear me? It's working? Okay, good morning, everyone, and thank you for the introduction. And I would like to thank the organizer for the invitation and bringing us together today. My talk will focus on advancing materials for CO2 capture and conversion, learning from operando and in situ experimentation. Before going to my talk, I would like to introduce you the people that contributed to this work, especially these three stars here on top: Margarita Rectina, Athanasia Tsoukalou, and Dawood Hosseini, whose thesis results I'm going to feature today. This is Professor Müller, the head of the Laboratory of Energy Science and Engineering at ETH Zurich. These are my colleagues that are experts on different characterization techniques, and of course, our collaborators here at the ESRF, Dragos Stoyan and Jakub Drek. In LESE, in our group, we work on developing materials and processes for closing the carbon dioxide cycle. And this is important when we think about a transition from a fossil fuel dependent economy to a sustainable one, in which we rely fully on renewable sources. Yet in this transition, while we still depend on fossil fuel, we must stop CO2 emission to the atmosphere. And we can do so by capturing carbon dioxide into material. We can do this from the air, or more efficiently, from large emission points. And this adds cost to the processes, but we can add value to carbon dioxide by converting it into useful feedstock. And we can do this via catalytic process. For example, we can convert carbon dioxide via the reaction with hydrogen, green hydrogen, and produce methanol, which is an important chemical and fuel. Another process that we work on is the dry reforming of methane that allows us to react methane and CO2 to major greenhouse gases to produce syngas, a mixture of CO and hydrogen that can be used in other processes. But these processes require that we advance our material to effectively capture or convert carbon dioxide. And of course, we need to learn how the material works at the atomic scale to be able to rationally improve our current formulation or design new materials. And as we all agree, a very powerful approach is to investigate model materials under reaction conditions to extract structural performance descriptors in combination, of course, with multiple characterization techniques to have a more holistic approach. So I'm going to give you 3 examples of applications in which we applied this concept. Going to the first one, capture of CO2 by magnesium oxide. So we can capture carbon dioxide by absorbing it into a material on the surface, or we can absorb it via its reaction with CO2 producing bulk carbonate. For example, calcium oxide or magnesium oxide can do this job. Magnesium oxide is particularly interesting due to the temperature range where it operates, between 250 and 450 degrees. And we can swing between 2 temperatures and capture carbon dioxide and release it for further use. And this allows us to, in principle, in theory, capture about 1 gram of carbon dioxide per gram of magnesium oxide, which is quite high. However, in practice, if you expose magnesium oxide to a stream of CO2 under thermodynamically allowed conditions for its carbonation, the actual uptake is very low, this dashed line here. And a solution to this drawback has been the addition of promoters, typically salts that under CO2 capture condition are molten. For example, here you can see if we add, if we add sodium nitrate, which is molten, and at 380 degrees, we can drastically enhance the carbonation of magnesium oxide. And how this promoter work? Well, this has been a question for several years in literature, and people have different hypotheses on how this material works. So some researchers says that magnesium and oxygen, so magnesium oxide, is dissolved into the melt, and it migrates to the triple phase boundary, where adsorbed CO2 reacts, and at the triple phase boundary, magnesium carbonate forms. Other researchers says that the surface carbonate of magnesium oxide prevent the CO2 diffusion into the bulk, and the molten salt, what it does is breaking this layer. Other researchers suggest that actually CO2 and magnesium oxide are both dissolved into the melt, and somewhere inside the melt, magnesium carbonate is formed, either like particles or really like a layer moving in depth into the bulk. So we wanted to address this question, and our approach was to understand how and where does magnesium carbonate form, is to use a model system, a magnesium oxide crystal 100, and we investigated the surface of this crystal under reaction conditions. This was done at ID 31. And we investigated this by X-ray diffraction and X-ray reflectometry. Here, briefly, what are the key observations from X-ray reflectometry? So the experiment was done in the following way. So we first cleaned the surface with helium, and then we pass carbon dioxide, and we observe the change. When magnesium oxide is not modified, so there is a bare magnesium oxide, we can observe the formation of a well-defined layer on the surface of magnesium oxide. When we look at diffraction, this does not give any peak. So this is a really below 1 nanometer layer that is non-crystalline on the magnesium oxide. Now, when we promote this material with sodium nitrate, we cover it completely. And the first observation of this material is that the surface became rougher. So this tells us that it's likely that the sodium nitrate is etching the surface, so dissolving the magnesium oxide surface. And when we flow CO2 over this material, there is a complete loss of a layer. We don't observe a layer, and it's a rough surface. So it's unlikely that magnesium carbonate grows as a layer when we add the promoter. So let's look at the diffraction data of the sodium nitrate modified magnesium oxide. So we observe indeed the reflection of magnesium carbonate, and what caught our attention is that it's not one single, but it's something in between a powder and a single crystalline material. So basically, the reflections are at certain angles, especially highly oriented. And we can also scan this reflection across the surface of magnesium oxide and locate the magnesium carbonate really growing inward and outward of the magnesium oxide surface. So it's growing at the interface. And if we regenerate this magnesium carbonate to produce again magnesium oxide, what we see is here it's polycrystalline. So there is no orientation of the magnesium oxide with respect to the magnesium carbonate. Very well. So we knew that then it was at the buried interface, and we washed away the sodium nitrate, and we could, in fact, visualize the crystal that were grown underneath the magnesium, the sodium nitrate. Further, here, Elena Willinger cut a lamella cut and could see that the magnesium oxide and magnesium carbonate is really close, and there is certain coherence between these two crystals. So we learn where and how magnesium carbonate forms. How can we improve, or how can we assess the structural parameters that govern the capture rate? And as I mentioned, these materials operate in cycles. And we move here to a powder system, and we investigated this at the beamline with in situ time-resolved X-ray powder diffraction. What we observed already in the lab is that the CO2 uptake was not constant during cycle. So here, simply the diffraction patterns where we can observe the magnesium carbonate form. And we took this large data set, we did some parametric Rydberg refinement and quantify the phases at each point, which allows us to also fit this with a kinetic model. So just to point out that with this, we can also calculate the CO2 uptake. And in the first cycle, we have a relatively high CO2 uptake, which dropped in the second cycle. And at the end, in cycle 10, we observed a reactivation of the material. So we can extract parameters that tell us about the performance and some structural parameters for each cycle and try to understand correlations here. So the CO2 uptake at the beginning high, then at the second and third cycles decrease, and later on increase again. So now from the kinetic analysis, we can also obtain a kinetic constant and an induction period. And we see that the kinetic constant that tells us how fast the magnesium carbonate form decreases in the second cycle. So basically this correlates with the uptake and gradually increases in the following cycle. So now, what could be leading to the deactivation part? Well, we thought if we need the magnesium oxide surface to nucleate the magnesium carbonate, if we have a decrease in the surface area of magnesium oxide, this could be one reason. So if we plot here the surface of magnesium oxide crystallite, so 1/d, we see a decrease, especially already at the initial cycle. So cycle 2 and 3 have the biggest drop. But it continues to decrease. So this is not the only parameter. And when we look close at the diffraction pattern, we observe a second phase that is being formed as we cycle. And this is a double carbonate phase, sodium magnesium carbonate, that is being formed from the melt and in reaction with the magnesium oxide, which increases over cycle. So with this, we hypothesize that this double salt here acts as effective and new nucleation seed for the formation of carbon. So with additional techniques, we studied this with in situ Raman spectroscopy. We learned that the molten salt, when we regenerate the material at 450 degrees, we start decomposing, which accumulates over cycles and this decomposition product react with CO2 and magnesium to produce this double salt. And this leads us to an increase in the performance. So learning from these studies is that we currently are investigating which are the most efficiency and how can we control in basically the pre-treatment or adding it via chemical method to further optimize the material. Very well, so we have captured the CO2, how we convert. I'm going to talk about catalysts for CO2 hydrogenation to methanol. A few studies we did some years ago here. So indium oxide has emerged as an interesting and promising catalyst for CO2 hydrogenation to methanol. Yet, before bringing this catalyst to industry, we must understand the structure and the reaction conditions. So our approach was to synthesize indium oxide nanocrystals and investigate them via combined X-ray absorption and X-ray powder diffraction under operando conditions at the Swiss Norwegian bridge. And to ensure that we are actually producing the reaction we claim we are producing, so producing methanol, we connected the outlet of our capillary to a GC that contains a FID detector and allow us to quantify the methanol with the similar time resolution as the SAS, the spectroscopy data. So with this, we can first look at the performance in the capillary at the outlet of the capillary. So this is methanol produced per gram as a function of time on stream. Initially, we observe an activation and stabilization of the material, followed by a stable performance, which later on it deactivates. Now, looking at the SAINS data, it tells us that there is a reduction of indium oxidation state on time on stream. Now, EXAFT data tell us that there is a change in local environment, indium oxygen and indium is decreasing in intensity. The magnitude of these spheres is decreasing. And when we look at the powder diffraction data collected in a quasi-simultaneous fashion, what we see is that the initially well-crystalline indium oxide nanoparticles or nanocrystals amorphize as the time on stream passes. So we can put all this information together again and correlate structural parameters with the simultaneously acquired methanol G. And what we learn from this is that the most active state of the catalyst correspond to an oxidation state of indium that is between indium +3 and +2. So it's partially reduced, meaning there is a formation of oxygen vacancies to compensate the charge. Yet, as under certain conditions, it can also over-reduce, leading to the formation of indium metallic. An indium metallic under this reaction is molten, which explains also the decrease in crystallinity. And what we propose is that this over-reduction is leading to the deactivation of the catalyst on time on stream. So the question we ask ourselves is, can we stabilize the oxidation state of indium via catalyst design? So we take a similar approach. We deposit the indium oxide nanocrystal, the same we have already studied, onto different metal oxides. And I'm going to focus on the most active one, which is when we deposit it onto monoclinic zirconia. And we see that indeed it stabilizes. And not only that, but it increases the methanol yield per indium cone. But why? Well, when we look at the SAINS data, operando SAINS data again, we see that indeed there is an stabilization of the oxidation state as we propose. So indeed, the zirconia is stabilized. What about the geometric structure? Here, the EXA gave us interesting information. So the indium oxygen sphere decreased slightly. This is possibly oxygen vacancies, but the second coordination sphere decreased more abruptly. And by EXAF modeling and by complementary technique, we find out that there is indeed the initially nano crystals of indium oxide are dispersed and incorporated into the structure of monoclinic zirconia, leading to highly dispersed indium sites, which are more stable and also more reactive. Very well. So this is the last example. So we have covered the conversion and the capture side. And now we have a integrated process. And in this process, what we integrate is the dry reforming of methane into a chemical looping process. So let me briefly introduce you what chemical looping is, and especially chemical looping for hydrogen production. So here it's a redox process. We have an oxygen carrier, in this case is iron oxide, and we can reduce it with, for example, syngas. And we can reduce it all the way down to iron, and then we can flow their steam to produce hydrogen. So this is thermal water. And we can close the cycle by oxidizing it again in air. To reduce the iron oxide, we need syngas. So we can, in principle, use the dry reforming of methane. So methane plus CO2 will give syngas. And we can use it in a different process. But what we thought is, what if we integrate these two processes into a particle level? And for this, we produce iron oxide nanoparticles that were covered with a shell of obsidian. And there we deposited platinum nanoparticles on top, which will act as the catalyst. So the core is the oxygen carrier, and platinum on Syria is the catalyst. We brought this to the Swiss Norwegian beamline again, and we followed the processes during the reduction stage with dry reforming of methane by diffraction, and also we did some extracts. But here I will show you mainly the diffraction due to time. In this case, we follow the reaction again. This is very important for us to correlate the solid state reaction with the gas phase reaction. And in this case, we use micro GC, which is faster than the FID one. And we are in the time resolution of below 1 minute. This is how the material looks like by electron microscopy. So you have the core of iron or iron oxide, the shell of Syria. And if you go into higher magnification, you see the platinum nanoparticle. The proof of concept is here. This is the diffraction data. So here we have Syria, initially iron 203, which get reduced all the way to iron via these two intermediates. And when we look at the gas phase, we see a high conversion of methane and CO2, but here in between we produce CO2 by the reduction of iron. And yes, so this basically proving the concept of the dry reforming of methane in the particle level. To further confirm this, we produce this similar material without the addition of platinum. And we did exactly the same experiment, and here you can see that we only go down to iron 304 we are not able to reduce in a dry reforming of methane the iron core, the iron oxide core, and actually this is also seen here in the gas phase. So we need the catalyst, and this platinum on Syria was very efficient in our purpose. So with this, I would like to leave you with the message that we probably all share, is that looking inside our materials with X-rays give us very important information for materials design. And in my opinion, it's very important that we focus on operando method and operando setup, which are as important probably as our synchrotron. And with this, I thank you all for the attention, and I welcome questions. If there is
Thank you, Dr. Abdallah, for this nice talk. We have time for a pair of questions.
Very nice talk. Thank you very much. Curiosity about the EXAFS analysis that you showed on indium nanoparticles. You showed that the diffractions, from diffraction, you see that they are amorphized, and you also see the decrease of EXAFS amplitudes. So in principle, there can be two things. You can decrease the coordination numbers and also increase the disorder. Did you somehow discriminate between these two effects? And because sometimes it's not straightforward. So how did you deal with this correlation problem? Thanks.
No, in fact, yes, I agree. So basically, if we only have the EXAFS data, I wouldn't be certain that this was due to morphism. So for me, this is why this combination of techniques become more powerful than each of them. And if you repeat this into setup, maybe you are not so sure. So we did different, of course, modeling, and we did the modeling with fixed coordination number and free the bipolar, and then free the bipolar fixed coordination number, and was way better with the free coordination number. Then you can free both of them, but then you get huge errors. And so if we stick to one model, then you can consider it the same is isothermal, fix the bipolar. At the end, that's what we did, but we did all.
Thank you.
Thank you for your question.
Other questions? No. Thank you again. And so we move to the next speaker. We have to change the PC, is right? Okay. So the next speaker is Dr. Alessandro Longo. He's a senior researcher at the Nanostructured Materials Institute of CNRR. And currently is also a beamline scientist at the ED20 beamline.
Okay. And this I have to keep in, right? Yeah. Thank you.
Okay.
Thank you, right? So thank you, the committee, to give me the possibility to share our work. And I start, you see from the title, the idea is basically follow the talk of Paola before. So to valorize the CO2 to produce more invaluable chemicals like ethylene. And then the idea is to stress, to mark the load Z elements that characterize the support. So ethylene is one of the most important commodity in the chemical industry, since it's very important to produce the material, plastical materials and fibers. And actually, currently it's produced by steam cracking of oils like naphtha and also ethane. And it's high demanding energy process because occurs at under 50 degrees, it's also pollutant. So of course we need to change this way of thinking. So an idea is then to use instead of the gas shale revolution, so the boosted the production of combustible gases like ethane and methane as well, to dehydrogenate the ethane directly. And of course, this you can do with oxygen, but oxygen is too strong, so there are over-oxidation that it's tough to be controlled. So the idea is now the role of the CO2 is that acts as a mild oxidant. And according to the reaction here reported, so it's a good one because it's a lower temperature. It's also carbon atom economy reaction because exploit all the carbon atoms. And this is an alternative process to this steam cracking. And of course, side carbon fission of the carbon can occur. So we need the catalyst to promote selectively the CH fission. And for this aim, typically the chromium catalysts are used with a good high conversion rate. However, the problem is chromium is also pollutant. If you want to change the ways to have a green, environmental friendly catalyst, the idea is to use atoms like iron. That is good. And for this proposal, the challenging of this research is to try to find the best catalyst to have a higher selectivity and also conversion. And the idea of that came up to our collaborators in the laboratory of petrochemical technology in Thessaloniki was to try to improve the production of this catalyst. And they did with using by sol gel method, they prepare a support and then with a reasonable area, they mixed together nickel and magnesium oxide and zirconium to give thermal stability. And on top of this, they created a catalyst by just impregnating with iron oxide. And then the aim of this part was to find the best compromise in the synthesis. So what is the best temperature and also the time that you need to do this calcination. Accordingly, they found a good catalyst with this kind of a percentage in terms of ratio of iron and nickel, and with a reasonable area as well. But if you look at the performance, it's clear that the best performance, the best catalyst is that one obtained at 700 degrees for 5 hours. That has a selectivity for the production of ethylene of 90% is quite impressive. In addition, the side-side carbon scission reactions, typically what's happening in a dry reforming ethane, are completely damped down, so very low amount. This is very interesting, but even more interesting is that if we look at the conversion as a function of time of stream, sorry. So we do see that there is a strong, I don't have the point. Okay, so the conversion increases from 70% to 90% as a function of time. And in the same graph, we see the conversion is basically around 21%. That it is quite interesting as well, from a physical point of view. So this means that self-activation are occurring, and these are definitely related to the structural modification that can occur during the reaction. So then we wanted to understand why and how this can be helpful to refine that catalyst in the future. So the idea, of course, is if you do typical laboratory techniques like diffraction, XPSR, they are not fully conclusive to understand what's happening in terms of metal oxide surface interaction. So then to establish a better structural reactivity correlation, and more advanced techniques are necessary. And of course, the idea was to use the synchrotron-based one, so X-ray absorption spectroscopy and X-ray Raman spectroscopy technique. So then to solve selectively the site, and so to look more closely to what's happening to the different atoms, so the iron, nickel, magnesium, and oxygen. So for the iron and nickel, of course, perhaps it's the good technique. For the low Z elements, the XRS seems to be the best because Okay, we know that the hectares, but concerning the Raman, the advantage is that we can use an high energy hard X-ray. This means that we can overcome all the problematic of the soft X-ray. Typically, we used to measure these low Z elements. And then basically, we can get a similar information we can get from a XNS part, especially when we go to small Q values. Since this is an elastic scattering technique, we can measure different angles of different Q. But for low Q, the two techniques are very similar. I would say so. The information is very similar, so we can distinguish the local environment of the scatter. So then, just we go to the result. So from nickel point of view, it's clear from the XNS point of view that there is no nickel oxide, and this is, so suggests that the nickel goes inside the structure to make an oxide, solid oxide solution with the magnesium oxide. And to confirm this, we did a simulation according to the DFT-based code like the MNES to reproduce the structure, since the XNS are sensitive to the multiple scattering pattern, sensitive to the three-dimensionality of the material. And so then we could we could reproduce quite nicely basically all the features except one. So then this strongly suggests that the iron goes inside and to create this mixed oxide solution. And then we try to give this kind of ratio of the nickel. In fact, we have 10% of nickel, so we cannot think differently like that. To even confirm this, we did a vector study. And since we use an exact approach, we could decompose the model by starting from the structure we proposed before, and just using two shells, we could fit our data up to 5 angstroms. That is quite interesting, but since the multiple scattering is the fingerprinting of the structure, we can easily conclude that actually the nickel goes in this kind of environment. And since the amount of the nickel is just 10%, we can also think that it's quite homogeneous distribution of nickel inside the oxide. Interestingly, after we do the used material, because we want to understand what's happening to the end, so we want to study also the used material, we don't see any variation on the nickel at the nickel edge. And basically, we can confirm the same structure of the nickel. So now we move on to the iron edge. And for the iron edge, we are interested to the difference of the temperature. And we see that when we deposit the material, the oxide on the magnesium, on the support, the nickel modified support, clearly we have an iron oxide. Basically, we can see two shells. And but when we do, when increase the temp, I don't know why that. This one what I want to show, but I don't know why it's happening. So when we got to 100 degrees, actually we see that second shell is increasing, and this makes sense with the temperature. But to have a better fitting, we see that some component is missing, and this component, since we have iron inside, probably inside the structure, means that maybe the iron starts seeing either the nickel or the magnesium. Since we could reproduce these differences by using a configuration in which we have a long bond connected with an angle of 120 degrees, this seems to be magnesium. So this means that the iron maybe is the magnesium atom in which magnesium should have a tetrahedral configuration. I don't know. Actually, I tried, but it doesn't work. So it should be the other one. I don't know. Sorry, I have to go back. That's fair. Okay, something is missing, but I don't understand why. So the difference of the first, no, it's not working. So the difference is clear when we look at the K space from the used, from the fresh and the used. And so now we go to the used material. So the used material, actually, when you do the catalyst, we see that there is a reduction of the material, the iron so gets reduced. And since we think that it goes inside the structure, again, we model the iron inside the nickel magnesium oxide structure. And also in this case, this works quite nicely. We have basically recovered all the main features. And again, we tested with excess analysis, and of course, this matches the structure we wanted to check. But in this case, again, to have a better satisfactory fitting, we need to add this blue contribution that is actually the that it's the iron that sees the magnesium, and the magnesium seems to be in tetrahedral configuration. So from the EXAFS analysis, okay, so the iron then, if you look at the K-space, they basically is the same environment of the nickel. It seems to be more disordered. And this is also clear from this kind of comparison. So then from this kind of analysis, we can have a strong suggestion that iron is, so goes into the structure, and it is basically the magnesium, and the magnesium seems to be in tetrahedral configuration. By looking again to the tennis part, we can also see that from the simulation, we don't have a strong free edge that disappear after the treatment. So this means that the iron goes inside the structure. It is basically is octahedrite, quite symmetric, that seems to be in the oxide. So then, to fully conclude about the magnesium coordination, we went to study the low Z elements by doing the Raman spectroscopy. And so this is the MgL23 edges, actually. And we do see, so respect to the MgO as a ref. And we see that there are differences. The difference is that the ratio of the peak is changing. And in the fresh already is changed, but in the used it's completely different, it's higher. So, and then in a previous paper, we conjectured that this difference ratio could be the formation of magnesium tetrahedral position. And then we did also oxygen, and oxygen, respect to the MgO, is also quite different. I would like to mark something about this, in fact. Oxygen actually averages all the possible cation you have in the material, right? So this difference that here seems to be small, actually are extremely important, because the amount of material, we have only 5% and 10% of nickel, so the modifications are quite important if you consider that basically you have magnesium atom around. And this modification seems stable after in the used material. So to understand this, of course, we need some calculations. And from literature, we know that from MgO oxide, we need to use a screening parameter. This means to make this long story short about the screening, that actually in magnesium, we have two different oxygen, one more reduced than the other. And but this is also, then we try to reproduce according to this approach, our material, again, using the MNES approach. And actually, we do see that the screening parameter reduces from 0.5 goes 0.3. And with this 0.3, actually, we can, in a way, reproduce the contribution that we have in the main resonance peak. This part is missing because it's zirconium oxide that it doesn't influence the reaction as well, in any case. So then we have this kind of reduction in screening parameter. This means that we interpreted it like that. So since the spinning is reducing, you have a much more electron available on the oxygen. And this means that the oxygen is more acid, if you want. So to confirm this hypothesis that seems to be clear from this calculation, we did the FTR and with adsorbed pyridine. And we see from the total acidity, actually, that it changes from factor of 10 from the fresh to the used one. So we can claim that lower spinning parameter means less basic oxygen atoms. This increases catalytic activity and also then increases selectivity towards the ethylene reduction. So this is extremely promising result, because in a way we can study the material from electronic point of view and to connect with the thermodynamical information. So in order to prove that actually oxygen sees a tetrahedral environment, we did several relaxed structures with quantum spectral calculation. So we tried the different configurations, but already you see from here that if you have the iron that in octahedral condition sees both magnesium in octahedral and tetrahedral condition, we have a quite nice reproduction of the data. So what to complete the scenario, we need to study the magnesium. And then, of course, from tetrahedral, so then the magnesium, of course, we again tried different structure, but the tetrahedral one, the that one here, reproduce basically the main features on the main resonance peak. So then, according to this, by combining again tetrahedral and octahedral environment, we finally could fit completely our configuration, and we could establish the amount of the magnesium in the two different configuration as a function of the different treatment. So for the used material, we ended up at basically we have 45%, 48% of magnesium tetrahedral. So basically, we can sum up a bit result. I don't know if I was too fast, but I think we need to go. So basically, we proved that iron oxide catalysts supported on nickel magnesium oxide zirconia modified are active and selective during the acid at the time determination reaction. And X-ray absorption spectroscopy, X-ray Raman spectroscopy evidenced that incorporation of iron to support is occurring, and that in addition that magnesium in the fresh material at 700 degrees has a 20% of magnesium in the tetrahedral coordination, and this become 50% in the used material, and the introduction of the magnesium in the structure induces a less basic electric oxygen upon incorporation. More interestingly, we see that there is this catalyst self-activation. Actually, if we time of strain, we do see that time of stream, we see that after 74%, we go to 90% after 6 hours, and this is also stable. And as this result, they are in a way that our catalyst that are here is respect to the chromium material, that is this one, are the better performance respect to the 4 iron gallium based material that are still that people is working on. So to do the conclusion of this work, we can say that the dynamic involvement of all constituent atoms in the catalyst is during the reaction. And this is like holy grail, if you want, of the catalyst. So we have to think catalyst differently. So we need to consider also support, especially for this kind of the reaction. And the incorporation of the iron oxide, that is another interesting point, buffers the basicity of the oxygen coordinated with magnesium in the support, resulting in high H bond scission selectivity. With this, I finished. So I would like to thank all the people that helped me, especially Stavros, that shared from the beginning the research with me, Christophe, that believe in us and give us in-house beam time to do this kind of experiment, as well Cyril and Olivier and Francesco da Capito at the LISA beamline. And then I would like to thank all you guys for the attention.
Thank you, Dr. Long. We have time for one question.
Thank you so much for the talk. I wasn't familiar with the X-ray Raman spectroscopy before. So can you do same as with XAS? Can you do the Fourier transform of the oxygen KH and see the the real space and the neighbors?
So to do Fourier transform, you need to collect like an XAS mode. Since when you do the region of interest in the spectrum, you have a different edges that can be there. You cannot do a long measurement, right? So then you are stick mostly in the, I would say, honest region. So then you cannot do Fourier transform. If you do a long scan, cover at least the K10 or whatever, yes, you can do. So in pure water, in pure carbon, you can do. But in mixed material, for instance, you can have also other edges that you can detect, so you cannot.
Thank you so much.
Thank you again. So, the next talk will be given by Dr. Nathalie Mangelik-Noël. She is a researcher director at CNRS at the Institute of Materials, Microelectronics and Nanoscience of Provence in Marseille.
Thank you. Okay, so thank you for the nice introduction, Frank. And good morning, everyone. So it's a very different topic from what you have seen this morning. I will discuss about silicon for photovoltaic applications. In fact, our team in Marseille is working on solidification, fundamental mechanisms of solidification and of crystal growth. And this is used for in many casting processes to, for example, fabricate turbine blades for plane engines, car engines, and silicon for photovoltaic applications. So here is a silicon solar cell fabrication chain from the purification of the material here to the fabrication of the PV modules. And we focus on this step where you fabricate the ingots, which are cut later on. And this is a solidification step. You have several processes that you can use, but basically this is solidification. And during this solidification step, you will create a lot of defects which have different scales from grain and grain boundaries. You also have twins and associated twin boundaries. Twins are grains with a very specific crystallographic orientation relationship. And you have an example here, not on silicon, but where you can see how it looks like in natural minerals, in a pirate mineral. And it's very important. It's very frequent in silicon when you solidify it, that you have different types of twins. The most frequent one is a sigma-3 one. It's a 60-degree rotation around 111 crystallographic axis. And it appears in model samples. This one is one of our model samples, but as well in industrial ingots. And the impact is here. Depending on the type of grain boundary or twin boundary you have different electrical properties at the level of these boundaries. Here is a random angle grain boundary, and it can be cured during the fabrication of the solar cell, which is not the case of this sigma 27 twin boundary. When you go down in scale, you have subgrain boundaries and dislocations. And also, there are very small defects, atomic scale defects. They will have an impact as well on the electrical properties. Here you have dislocations that developed during the growth of an ingot in a casting process where they use some monocrystalline seeds at the bottom, but as they are very big ton ingots, you cannot have a very big monocrystalline seed, so you use several of them, and you have some edges between these monocrystalline seeds and the formation of dislocations here, and it degrades the electrical properties here. And on top of this, you have impurities that come from your initial silicon feedstock or your furnace environment and the crucibles. And the impurities will create specific defects, as you will see in the following, in my case study on carbon contamination, and also segregate at the level of the structural defects. So what is the originality of our approach is that we investigate these growth mechanisms using in situ and time result X-ray imaging during the solidification, and we use two techniques, radiography and topography, at high temperatures up to 1,800 degrees C in our furnace. So first, or at the same time, we perform X-ray radiography together with topography. So how do we do? I will briefly present these methods. Also, maybe most of you know very well these kind of methods here. But maybe you can understand better how this is organized together with our solidification furnace. So the sample is inside our two resistive heater solidification furnace. Here is at a higher temperature than the melting temperature. So it's liquid, and here at a lower temperature, so it's solid. And we shine the X-ray through the sample during solidification, and the contrast we have in radiography is an absorption contrast for metallic alloys. So it will depend on the type of elements we have during solidification. Here you have the solidification of an aluminum tin alloy. The primary phase is made of aluminum. It's lighter than tin, which is rejected in the solid region here. So the liquid region is darker. In silicon, we have to rely only on the density differences between solid and liquid. And this is why we get this contrast between this solid region and this liquid region. With this, we have an information about the solid-liquid interface in situ and real time, its morphology and its dynamics. This kind of experiments can in fact be done in laboratories if you restrict to lower temperatures, 600 degrees C temperatures. But if we want to go to higher temperatures, if we want to perform topography at the same time, we have to do this at ESRF, and with using synchrotron sources. And in fact, we do this at ESRF at the ID19 beamline. So what do we do at the same time as we record the direct beam to have the radiography? We also record the diffracted beams here, and we have a look at what we have inside the diffraction spots, which is a topograph. And then we get some key information, complementary information about the crystallographic orientation, the distortions, defects, and misorientations in our samples. And recently, and this is together with the ID19 team, we improved the time resolution during this kind of experiments. Initially, we recorded these topographs on films. And now we can synchronize several cameras that focus on these topographs with sufficient resolution, spatial resolution. And this is what we get here. What you see here is a monocrystalline seed. It's the topograph. You see the propagation of dislocation groups while we are heating the silicon seed. Then we will melt it partially and start solidification from this monocrystalline seed. And what we follow is the dynamics of the dislocations during all these phases, heating, solidification, and later on cooling down, the interaction of the different defects. And here, for example, you have the formation of the twin boundaries I've already mentioned. And we try to understand the interaction of all these defects. This is the right place. Maybe I just want to thank the ID19 team with whom we've developed this new, recent and new progress. And now we have really some more information about the dislocation dynamics, which is really a key issue for the solidification of this material. So we use also another method here as well at ESRF, but this time at BM5. This is done ex situ, so after solidification. This is working curve imaging. In this case, the sample is on a goniometer, and it is oriented so that we select a particular family of plane. And then working curve is done around the bright angle, and images are recorded all along the working curve. And what you obtain is this for each pixel, this type of curves here. And the integrated intensity is very similar to what we have in topography in situ, but we can also have complementary quantitative information by adjusting here the curve, fitting it. When we measure the full width half maximum, it gives quantitative information about distortion and the peak position about local misorientation. So here we apply this to the effect of contamination of silicon with carbon, what happens during its growth or solidification. So we have a model sample with only contamination with carbon here. and we follow its solid-liquid interface during solidification. This solid-liquid interface in these conventional conditions of temperature gradient and cooling rate is smooth. But what you can see is that at the edges here, we have crystallographic facets and regular nucleation of grains at the level of these crystallographic facets. In fact, the grain structure at the end of solidification looks like this, where you have indeed the formation of grains on both edges at the level of the facets, which are here regularly during solidification. But if you compare this to what happens during the solidification of pure samples, in pure samples, you have only a single alternation of crystallographic orientation and only the nucleation of sigma-3 twin boundaries, which is not the case with the contamination with carbon, where we have the nucleation, and we can say that we really have the nucleation because we have the in situ images of higher order twin boundaries during solidification. So now, during the same experiment, as I mentioned, we also record the topographs, and here are the topographs for two diffraction spots, so two family of planes. We can see, in fact, several defects and features. I will focus only on two of them. So first, coming back to this very particular formation of higher order twin boundaries, what we have during solidification and after cooling down on the topograph is this type of images, which in fact characterizes the bending of the crystallographic planes at the level of these higher order twin boundaries. And this can be related to the lower crystalline quality of this type of twin boundaries that are also incoherent, meaning that you have dislocations inside these twin boundaries. So this unusual twinning, which is less favorable from the energetical point of view, can happen when in the presence of carbon, and it is due to nucleation during solidification. And it's also, it goes with the lower crystalline quality dislocations and distortions at the level of the twin boundaries. I will focus on another defect. So here I just show these regions for the two spots, but in fact it's all over the sample. It's these black spots here, and we will see how we can characterize them. So they appear during solidification, but they are also observed after solidification. So they remain after solidification, and we wanted to characterize them further using the ex situ, the working curve imaging at the same place as what you've seen in situ. And in fact, they are characterized by localized distortion all over the sample, but as well subgrains as can be seen on the peak position map. We wanted to know if this is only a surface defect because we project our images during solidification, but with working curve, you can also use a variation using slits. But here you have 3 slits that project what you have within the thickness of the sample. So the entrance face is here and the exit surface is here. And what you see is that we find again the same type of defects, and we measure exactly the same value for the misorientation. And this is not the case. I have to say that just show a single other result. It was not only in our model sample, it was also observed in several samples containing carbon and characterized during solidification. And for example, this is the case of a NAS-grown industrial silicon sample with a very specific method based on the use of a carbon layer on which silicon is grown like this by pooling. And again, we found the same type of defects and they were characterized with the same quantitative values in fact. So with all these results, we propose a mechanism for the formation of these defects during solidification. Due to the low solubility limit of carbon in silicon, you have the precipitation of carbon silicon carbide during solidification, close to the interface or at the solid liquid interface. Then at the level of this precipitate, the interface is slightly in advance compared to what it's going from the seed here. And you have the formation of these distortions of the crystal. And at the same time, because you have several of these precipitates all along solidification, we characterize them everywhere in the sample, you can have the formation of these subgrains or local misorientation. So as a conclusion, when carbon contaminates silicon during solidification, you have the formation of silicon carbide precipitates, but also the nucleation of higher order twins. So you already have defects at the level of the twin boundaries, but also local distortion at the level of these small features I showed to you and subgrains. And all this will have an impact on the properties of the material when you want to use to fabricate solar cells. The precipitates give some difficulties for wafer cutting and also induces locations. These higher order twins will have our sites of recombination of minority carriers and degradation of the electrical properties at the level of the grains, and same thing for the smaller scale defects. So as a prospect and ongoing work, so we want to study the impact of other impurities. This is really a key issue in this sector, especially when you think about recycling of silicon, which is coming now and industrialized. We also want to continue the study about subgrains. We have some phase field modeling in the team, and compare our feed simulation work with our results. And with this, I thank you for your attention.
Thank you. We have time for one question.
Maybe I missed it, but can you see the silicon carbide precipitates also
No,
using?
not with this method. We cannot
Okay.
see the silicon
But in
carbide.
principle,
No,
is
we
this...
measured, in fact, after carbon localization at the level of these black spots, and yeah, so we check this later on. We cannot see the silicon carbide.
Thank you again. And so we can move to the last speaker. He's Dr. Quentin Jacquet. He's from CA of Grenoble. Remarkably, last year he received the Young Investigator Awards at the International Operando Battery Days Conference. Now we are waiting to everything changes. Okay.
Okay. Okay, well, good morning, everyone. Thank you for staying for the last talk of the morning. And so I'm going to talk about batteries, I guess introducing the afternoon, and especially focus on looking at lithiation heterogeneities during high rate charging. So a very classical introduction about why we study lithium-ion batteries, and I think it's well reflected by this graph here, which is showing the demand of battery in the past and future by application. You can see that there is a huge growth, which is coming for battery, especially for electric mobility. So the reason why we study lithium-ion battery is because there's going to be a huge market for that. And for electric car, one of the main issues is to be able to fast charge this battery. And fast charging leads to out of equilibrium reactions, which I'm going to describe here. So basically, this is a schematic of a lithium-ion battery with the color being proportional to the lithium concentration. So you have your lithium in your electrode at the beginning of your charge, and as you're charging, lithium basically travels from one electrode to the other one. But if you fast charge it, you're basically going to try to pull off lithium from your material faster than it can diffuse it in it at the different length scales. That's going to create concentration gradients at particle in the liquid and at the electrode scale. And this is detrimental for the performance of your battery. For example, if you try to stuff lithium into graphite too quickly, you're basically going to saturate the surface of lithium, and the next lithium you want to put in is actually going to plate lithium metal. And this lithium metal is going to react with the electrolyte, and you're going to lose lithium, which is not going to be available for the reactions anymore. Another effect of this fast charging would be losing part of your electric capacity just because this part of the electrode is inactivated. So if we want to understand better what's happening, model it better, we need to look at it better. And for that, we need spatially resolved and fast operando experiments. Obviously, when we think about fast and spatially resolved, we think about large-scale facilities, and there are a few beautiful examples of the literature on how you can look at concentration gradients in batteries. So at the APS, for example, where they studied both graphite and NMC materials. Examples at the ESRF on ID15A, where they look at very fast charging in the presence of lithium plating, or examples for neutron imaging, for example, in Oak Ridge. And these beautiful experiments give us a qualitative insight on mechanisms, but from the authors themselves, it is still not quantitative when comparing to modeling, which means that we're still limited in our capability of predicting the performance of these batteries using modeling. So how can we bridge between experiments and modeling? And one way we think of doing this is really by integrating our experiments together with simulation and standardized samples. So this is what we're doing in the Big Map project, which is a European project devoted to basically trying to make the link between all these different experts. And so in this context, when we wanted to look at fast charging, we started making an experiment wish list of what we needed to measure in order to have a full picture of the electrode. And so we needed to have microstructure of the electrode, nano and microstructure of the electrode, and also concentration gradients imaging. So if we want to make these 4 experiments in large-scale facility in a reasonable short time, that's pretty hard, and that's been possible thanks to the battery pilot hub that Sandrine introduced yesterday. So we've been able to do most of the experiments in less than a year, and 3 of these experiments at the ESRF, 1 in the ILL, and then the Wednesday today. And today I'm especially going to focus on lithium concentration imaging using these 2 techniques. So the idea of combining the 2 techniques, which are the micro-XRD imaging and the neutron imaging, is that they're very complementary. So I'm going to show you why. And to be able to correlate these techniques, you need to measure it in the same sample. So we basically have this Schwarzschild cell, which we can bring at different beamlines. And inside the cell here, you basically have your electrochemical stack composed of commercial electrodes given by our commercial industrial partners in the project. And so we first go to ESRF, where we do micro-XRD. You basically have a microbeam, you scan it along the electrodes, so both the electrode, the anode, and the cathode. And so this schematic represents how we're scanning our electrodes. We're basically taking this 5 by 40 micrometer beam, and we're scanning in the depth of the electrode and moving around the electrode to limit damage. And for each pixel, we get a diffraction pattern, and for that, we can indirectly get lithium concentration. The other technique, which is the neutron imaging, is we're using a wide white neutron beam. So we're illuminating all the cell, and we're getting this radiographies where the contrast is proportional to the lithium concentration. So in this image, for example, you're seeing the LNO electrode, which when the battery is discharged, is the electrode containing the lithium that we've cleaned up. So a bit more details about the neutron imaging experiments. Just before that, we cycle the cell at different C rates to look at the impact of the charging speed, charging and discharging speed on the heterogeneities in that voltage range. So very briefly, the way we analyze the pattern is using two different methods. So we do a single fit fitting using Prisma, which is an app that's developed in this big map project. Main advantage that being very fast, and we also perform a multi-phase sequential Rydberg refinement, which is more precise in terms of giving all cell parameters and also much more easy to handle pick splitting that we have during the monoclone distortions in LNO. So the cell parameters that we get are shown here for the different C rates for LNO. So briefly, the structure of this material is a layered structure. So you have layers of lithium and layers of nickel. And when you remove lithium from the material, you basically have the layers separate each other and then shrink. And that's represented in the C parameter variation with the lithium content here. And what we're getting at different C rates is fairly in a good agreement with what has been reported before. And that's a similar thing for graphite. It's also a layered material, which interlayer spacing vary with the lithium concentration and forming different stages. But again, the message here is that we can get very comparable results with what has been done. Once we have the cell parameters, we can get the lithium concentration by using calibration curves. And then we can map the lithium concentration and more specifically the heterogeneity in lithium concentration in the depth of the electrode. So this graph here, this map here, this is the electrode depth. So we're basically looking at the center of our electrode, and the high values of electrode depth are close to the separator, and the low value are close to the current collector. And then this is the capacity. So in this graph here, you have the voltage and the average lithium concentration in graphite versus the capacity. And the color represents the deviation of the local lithium concentration with the average. So what you see basically, as you're charging graphite, you're basically putting lithium in. And you can see that you find more lithium at the separated surface of your electrode. When you discharge, you're basically removing lithium, and you can see that this concentration gradient flips. And then as you charge and discharge at different C rates, you can still see the flipping of the concentration gradient. And you can also see that the concentration gradient becomes more and more intense. For the LNO electrodes, the cathode, we basically see the same story. But if we look at quantifying the concentration gradient, we can do that by integrating this deviation to the average. And this is basically represented by this NAD. Basically, the highest this value, the more heterogeneous your electrode is. And you can really easily see, comparing the graphite with the LNO, that graphite is much more heterogeneous than LNO. And second thing you can see is that for the graphite especially, the charge seems to be less heterogeneous than the discharge, and that is true for C and 2C. So now if we take all of these observations and try to understand if they make sense or compare them to the literature, well, the two first ones being that the reaction starts at the separator surface and the reaction heterogeneity increases with C rate is, is fairly well described in the literature. This is a simulation of a lithiation on the real electric structure, and you can see here the lithium concentration in the solid phase and here in the liquid phase. And it's well known that at high C rates, you're limited by the lithium diffusion in the electrolyte phase, which basically means that you have less lithium in the electrolyte at the bottom of the electrode, and hence your reaction is limited at the bottom electrode because of that. Now, the heterogeneity being stronger in graphite compared to LNO, it's less clear in the literature why that could be. So this is one of the explanations. So what you have here is a simulated NAD with respect to the lithium concentration in graphite. And my point is that the NAD is increasing in black. The NAD is increasing where the electrochemical profile in blue is flat, which is explained by the fact that when the electrochemical profile is flat, you have no driving force for homogeneous system. And so your low heterogeneity perhaps. and the electrochemical profile of graphite being much flatter than the LNO, and we can rationalize why one would be more heterogeneous than the other one. And finally, the graphite discharge being more heterogeneous than the charge. I mean, this is not something I could find modeling for. I'll use the same strategy as before. Okay. I have a video in the next slide. All right. Right. What I wanted to say to finish on that slide is that we can find data. We can find data showing the same things, that the discharge is more heterogeneous than the charge, but not modeling results. So I'm going to show you more data going into that sense. And that comes from the neutron imaging experiment. So just to remind you, the type of data that we have, no, I'm not going to remind you the type of data that we have. But you can imagine we have videos basically of lithium concentration in our electrodes. And from the video, you can also, right. So we get these videos where we can see basically the black going into one, the other electrode, etc. And you can analyze this video and basically get an NAD obtained from the neutrons, and you can compare that to what is obtained from the XRD. And qualitatively, you can see that again, we find that this charge is much more heterogeneous than the charge. So a lot of independent data sets showing the same things, and looking forward and still trying to understand why that is. Which bring me back to our coordinated workflow, where we hope to get some inputs and disseminations on that question. But now I'm going to just show you what we're doing in terms of looking at the electrode nanostructure and microstructure very briefly. So we've been looking at different scales, so in nano tomography and microtomography at operando and ex situ conditions for both the electrodes. And this is something that's being done with François Cadieux. So if you, I mean, the poster is not here, but if you still have questions about it, please ask him. Right, and finally, I would like to conclude by saying that fast charging is not the only scientific question that we look in Big Map, and therefore it's not the only experiment that we've done. We're also looking at fingerprints of SCI components using XRS, or electronic structure of LNO using RIX. So with that, I really would like to thank all the collaborators and all the BMAN scientists participating in these experiments, and thank you for your attention.